Record. All right. So here we go. We started talking about ANOVA yesterday, and then I snagged these guys. I'll bring them in a bit. We were going through an ANOVA example, which will be a nice way to review, I guess. But maybe just a little bit of review. 2 lines I gave myself. I'll need more, I can tell, but that's okay. So we started talking about ANOVA, which is analysis of variance. Kind of confusing, the terminology, just because we use an ANOVA to compare more than 2 means, right? And so to compare means across more than 2 groups. Okay. It doesn't tell us, so one thing to remember about the ANOVA is it doesn't tell us which group is significantly different. It just tells us if there is something that's significantly different. I knew it. I'd need to. This is where we started, or we ended last day. We just had time to bring this in, and then I was out of time. The null hypothesis for an ANOVA, right, is that all the means are the same or not significantly different from each other. So you can write that out in words, but I prefer notation using mu. Mu1 is not significantly different from mu2, is not significantly different from mu3, all the way up to mu k. And this is a good place to remind ourselves that k is the number of groups, right? So more than 2 groups. So k is the number of groups. Now, the alternative hypothesis is that at least one mu I does not equal mu j, where of course I is not equal to j. So one thing to kind of remind yourself of here is that even if you reject H naught, right? So if you find a significant ANOVA is usually the terminology that we use. So even when an ANOVA is significant, which I haven't used explicitly, but you should know just kind of by context really, that really what I'm saying is if you reject H naught, I'm gonna bring this smaller. So if you've rejected H naught, then at least one mean is significantly different from at least one other mean, right? And so we will not know which mean, so potentially more than one, right, are significantly different. I had a little pile up here. Okay. Now I want to start a slanted end of review sign. So we did introduce the table, the ANOVA output as well, but I'll run us through it again once we see it here. So just hold tight. Okay. Little copy paste pile up. Okay, here we go. Put it on a fresh page here. Ah! There. All right. The conditions for an ANOVA are the same as for t-tests, with the extension of we have to have roughly constant variance across each of the groups, right? And so the first condition is independence. We are talking about now, the bad part is I know nothing about baseball. Even MLB, I'm just relying on it saying baseball down here. So that's how bad I am at sports things. But we would like to discern whether there are real differences between the batting performance of baseball players according to their position, outfielder, infielder, and catcher. And I don't like this question because it's sports related, but also I like using this question because they go through and they have the solutions in even more detail in the textbook. So if you want to fill in the gaps, then you can. So for independence, what are we assuming? We have to assume that the groups are independent of each other, right? But we also have to assume independence within each of the groups. We are going to just have to assume it. I don't think. Yep. Okay.
So we're not taking the whole question. That after?
I just cut it
Oh, okay.
because I think it just outlines in more wordy ways. Let's see here. Where is it? We'll use a data set called BAT18. No, we won't, which includes batting records of 429, blah, 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 blah. That's why I cut it. It's too long. You can keep it if you want. So we assume the groups are independent of each other. And that players within each group are also independent of each other. That players within each group are independent of each other. Normality. The sample sizes for each group, let's see here, I have are quite large. And so here's the sample size for each group, 160, 205, and 64. And so those are all greater than 30. And so I'm just gonna have to assume that there are no outliers, no extreme outliers. Even with sample sizes this large, we would be able to handle pretty extreme outliers. So that's why it's no longer a concern anymore. The smallest sample size is 64, which is the catchers. So we can assume, so we may assume normality, right? Why? Because n is greater than or equal to 30, right? For each of the groups. So it still hinges on that. But once you've reached a sample size of 30, you're allowed to relax the normality condition quite a bit. We can handle extreme outliers. Okay? It also happens that they included, let's see. What's another way you could check normality, right? Back to basics, you could make histograms. So here, like I said, they check the conditions more thoroughly in the textbook on page 291, and that's where we could have a look at the histograms and just convince ourselves that, hey, everything looks approximately normal, right? The most extreme, which isn't even that bad, outliers here in the outfielders, and it's still kind of within the data range. Okay, so I'm not concerned. The constant variance condition is the only new condition that only applies to ANOVAs. And so constant variance we saw the side-by-side box plots, and you know what, I'm going to bring them in as well. But what's another thing that we could do? Constant variance is talking about the variability. The standard deviation is a measure of variability, right? So if the standard deviations are roughly in the same realm, then we can assume constant variance. And so here, right? Standard deviations are measures of variability. And it even says, notice that the variability appears to be approximately constant across groups. 0.043, 0.038, 0.038. Right, two of them are actually the same. 0.043 is similar, so we're good. So since the standard deviations across the three groups are similar, we may assume constant variance. It's a state of mind. No, it's just, you're just eyeballing it. Remembering that your goal is to argue that you have constant variance. Otherwise, you can't do the test, right? So I feel like humans naturally, we want to say, oh, no, that's not true, right? 0.043 might be different from 0.038, and that's true. But in this case, we kind of want to take the different approach and say, I don't know, close enough, right? Because that's one of our arguments for using the ANOVA. Depends on how hokey you want to be. There are other hypothesis tests that you would do. So you can do a hypothesis test. So are these, right? It would be kind of the same deal, right? Are these significantly different from each other? But that's beyond this course. It exists, right? And so then you would go ahead and you would do another hypothesis test to test if these are significantly different. And you're hoping that the answer is no, they're not significantly different, right? Because then you can go ahead. And same thing for the normality condition. You can also run a hypothesis test to check for normality. And so there are hypothesis tests that you can do for a lot of these conditions that we don't get into here. Yeah.
Sense of like being in our course when we see ANOVA, we can just we have to look at it.
We have to argue that it's constant.
But like, I assume we're not really going to be asked questions situations where one of them is like 200 and the others are 0.0.
No.
Then, like,
And if that's the case, then you would say, well, I can't do an ANOVA, right?
Yeah.
That's all I expect of you. Yeah, but here, they're
Short
relatively the
question.
same. Huh?
You give us a really short question.
Yeah.
That's just like, do an ANOVA on this.
I mean, it is something that you're supposed to know, but I would want you to go ahead and do the ANOVA after. So usually the assumptions check out for us. Yeah. It could be one of those questions, why can't we do the ANOVA here? Right? And then, yeah. Since the standard deviations across the three groups are similar, we may assume with constant variance. We also saw this visually, right? Let's see here. Where are those little side-by-side box plots here? Oops. Right, so visually or visually, we can check, right? And you're just going for the main blocks because the outliers are only 1 or 2 points. So even though, you know, they're concerned for normality, they're not so much a concern for the constant variance. And so here, these are roughly the same width. I guess it's height, but I call it width. Okay. So you can check it. I'll bump this over here. Wait, no, I won't. You can check it visually if you have the side-by-side box plots. But if you only have the standard deviations, then you would just check the standard deviations. And if you have neither of those, you would argue that you're assuming constant variance across the groups until you're able to check it.
Okay, so it is one of those things where like we don't necessarily have to have either of those things, and in that case, we can assume like a dependence that.
Yeah. So then, but then you have to say, hey, here's one of the things that I'm assuming, and I haven't been able to check, but I am assuming that I have constant variance across the groups. Nice. Yes. All right. Therefore, the conditions for inference are satisfied. Woohoo. I think we wanted to know, what was the initial, whether there are real differences between the batting performance of baseball players according to their position. Okay, and so for ANOVAs, what's nice is there are no confidence intervals that we're going to do. We're just doing hypothesis testing, right? Is there a difference in the means between these groups, or is there one or more that's significantly different? So our step 1 for the hypotheses or the hypothesis test is state the hypotheses. Getting ahead of myself here. Bump this down here. The null hypothesis. Now, what I want to do is just give you the option. You're allowed to write it out in words if you want to. And did I even bring in the formula sheet? I don't think I did. Here. So on your formula sheet, you're going to have, and maybe what I'll do because I'm pretty sure I didn't bring in the formula sheet last day, so sorry about that. On the formula sheet, I give you the null and alternative hypotheses, and also the ANOVA table and the relationships. Okay. So a key thing to remember is what K is. K is the number of groups, right? Because here you list your mu's up to mu K. Here your degrees of freedom 1 is K minus 1, right? And then N minus K. So a lot of it is relying on you knowing what K is. And I didn't put it on the formula sheet, so that's rude. Yeah. But now let's use the formula sheet. Now we can do step 1, state the hypotheses. I'm first going to use the formula sheet version, and then I'm going to write it in words. You're welcome to choose whichever one you prefer, right? So whichever one comes more naturally, but remembering that the one in terms of the mu's is the one on the formula sheet, right? So, but sometimes we prefer words. So mu, what were my groups here? Let me see if I can. Outfielder, OF, is equal to mu IF, infielder. There was an inflection there, I don't know. Is equal to mu C, the catchers, that group I know. Okay. Let's just make a note to ourselves that here K is equal to 3, right? I have 3 groups. Okay. So now my alternative is that at least one of these mu's, and you can write it exactly like it is on the formula sheet, at least one mu I is not equal to mu J, where I is not equal to J. Seems like kind of a silly condition, but K is the number of groups.
Right.
Or in words, if you prefer, the null hypothesis is that all the, let's see if I have it somewhere here. Do I have that? Or do I have to scroll up? I don't want to scroll up. I'm gonna have to. Okay. The batting performance of baseball players does not differ across the position. Let's see. The batting performance and I'll just say the mean because it didn't actually say, or maybe I'll just bump it in here. I'll make it proper. The mean batting performance is the same across the groups. Whereas the alternative is going to be at least one mean is significantly different from at least one of the other means. At least one mean is significantly different from at least one other mean. Step 2, do the test. For the ANOVA, what I'm going to get you to do is if you've checked out the assignment that I posted, maybe not because we haven't finished the section, so it's totally fine. But what you'll see is that there will be a table that's partially filled in. And so you'll need to fill in the rest of the parts. One thing that I will give you is the p-value. So you don't have to find it because that's hard by hand. It would need another table, and I don't think that that's necessary. I'm just going to give you the p-value. Okay, but you need to know what to do with it, right? And so you'll have a partially completed table, and you'll need to know the anatomy of the table, which I give you on your formula sheet, right? So, all right. So doing the test is going to be fill in this output. It really is calculate the F statistic, right? So your test statistic is an F in this case for ANOVA. And so you really, the goal of the operation is to find this F value. Now, the bigger F is, the smaller is your p-value. So that's the same as the chi-squared, as your t's, as your z's, right? The larger it gets, the smaller your p-value gets. F close to 1 means that there's no difference really between any of the groups. Okay? But you'll have the p-value, and that's what you'll latch onto. Okay? So in this case, right, if we go and we look at our degrees of freedom, so the numerator degrees of freedom or the group degrees of freedom, DF1, is k minus 1, right? The number of groups minus 1. So we had 3 groups minus 1 makes 2 degrees of freedom. Right? The residual degrees of freedom is n minus k. So we had a sample size of 429 minus 3 makes 426. And then we could find the totals down here for the degrees of freedom and the sums of squareds if we wanted to. The sums of squareds, so here you could have a total, which is 2 plus 426. And how about I just do it? 428, which is just n minus 1 again. Oh, that's the pooled, never mind. And where's my trusty calculator? I'm just gonna add up these sums of squareds. 0.0161 plus 0.674 is 0.6901. Right. The rest don't get totals because we don't really need them. You can find the total mean squared, but usually these are the ones you're relying on. And how I start you off is I give you 2 out of the 3 of the sums of squareds, and then you have to find the third one, and then you use that to find the mean squared, because how does the mean squared work? It takes the previous sums of squareds divided by the degrees of freedom on each line, right? So this divided by this is this. And then to find your F, it's the mean squared for the group divided by the mean squared of the residual, right? And that's all on the formula sheet. So step 3, find the p-value. It will be given in the output for ANOVA. of course, you could use R, there is an F distribution, but because it has two sets of degrees of freedom, right? The numerator degrees of freedom and the denominator degrees of freedom. And so it's kind of a big clunky table if we're doing it by hand. And that's why we're not doing it. So here, the p-value is 0.0066, right, from here. That's easy enough. We can do that. Oh, a new page. Step 4 is your conclusion. This p-value is very small, right? It's less than 0.05. We weren't given an alpha level, that's okay. We just use 0.05. So we have enough evidence to reject H naught. Okay. So since the p-value of 0.0066, this is our first time that we actually have a p-value to give, right? That's always the case, but for our working with tables and stuff, we haven't been able to do this. So now we just have a p-value, that's great. So since the p-value of 0.066 or 0.0066 is less than the assumed alpha level of 0.05, we have enough evidence to reject H naught. In favor of HA. Therefore, what can we say? Not much, right? The mean batting performance in at least one of the groups is significantly different from at least one of the other groups. Right. Therefore, the mean batting performance in at least one of the groups is significantly different. Whoops. From at least one of the other groups. Oops. An obvious follow-up would be, well, which group, right? So here, okay, we've decided there's at least one of these groups that's significantly different from at least one of the other groups. Great. Do you mind telling me which one? Then we say, sure, but I'll need to do another hypothesis test. In fact, I'll need to do 3, right? And so now, okay, and so once you've run an ANOVA, if you found a significant ANOVA, it's very rare that you only care if there's something different, right? If you find that there's something different, you usually want to know which group is significantly different from the others. Okay, and so that's what we call a post hoc test, right? It's post hoc, which is after the fact. So we've already run an ANOVA, we've already decided, hey, there's something going on. So then as a follow-up, what we do is we do the pairwise comparisons. Okay, so here, which position, and I'll make it plural potentially, which position is /are different
And so when doing that, I'm conducting the 3 hypothesis tests.
So now we conduct a post hoc, which is after the fact test. So post hoc is means after the fact, and a post hoc test is basically a follow-up test. Okay. And one thing that I do want to kind of warn you about is that there are many different post hoc tests that you could do. Okay, we are going to do the most kind of the easiest, also common, the most common, because we already know how to do it, right? We need to do a 2-sample t-test for the 3 combinations that we have, and we can do that, but with a slight adjustment, and it's called the Bonferroni adjustment, which is fun to say, and so here we go. But I do want to warn you that there are many different post hoc tests. Okay. But we will use the 2-sample t-test since we already know it. Okay. I'm not going to get you to do the follow-up tests, but just as a side note, you would use the pooled standard deviation and the adjusted degrees of freedom. And so that's what I'm not going to make you do that, okay, because I don't want to introduce it. But you should, so I'll make a note of it. But here, I'm just going to tell you what to do, and then we're not actually going to do it. Okay. So here, let's see. In the pairwise t-tests, we would use the pooled standard deviation to find the standard error. We won't be calculating the t's. The test statistics. But you would. The main adjustment that we would make when we're doing these pairwise comparisons, remember, we started off and we said, well, you might be tempted to do these just 2 independent sample t-tests times 3 to compare A to B, A to C, B to C, right? And that compares all the different combinations, right? But what happens is every time that you run that test, then you introduce the alpha level, so 0.05 probability of making a type 1 error, right? And a type 1 error is rejecting H0 when you shouldn't be rejecting it, right? And so that's a problem. And so to get around that, what we do is we make this Bonferroni adjustment, which is the simplest adjustment where we just take our alpha level and divide it by the number of pairwise comparisons that we want to make. And so 0.05 divided by 3, and then that's your alpha level, right? Making it harder to reject H0, but that was the goal, right? And then once you have done all the tests, then they would add up to 0.05. Okay. And so the main adjustments we will make is to calculate the adjusted alpha level to use for each pairwise comparison. I'm going to grab it from here. Where's that Bonferroni? Nope. And here. So multiple comparisons and the Bonferroni correction for alpha. So when we're testing many pairs of groups, then it's called multiple comparisons. So the Bonferroni correction suggests the more stringent significance level is more appropriate for these tests, where we have this alpha star, which is going to be your adjusted alpha level, which is the original alpha level, 0.05 usually, divided by capital K, where K, capital K, is the number of comparisons being considered, either formally or informally. Okay. So if there are K groups, so lowercase k groups, then usually we compare all possible pairs just in case, right? There's no reason not to with software especially, okay? And just in general, if you have K groups, then you would have K times K minus 1 divided by 2 comparisons, right? So for us, we had 3 groups, so 3 times 2 divided by 2 makes 3 possible comparisons, which we saw, right? That's easy to kind of wrap our head around. Yeah. And so, for example, we had K is equal to 3. So then K is 3 times 3 minus 1 divided by 2, which is 3, right? A to B, A to C, and B to C. That's a little bit harder, right, to kind of wrap our head around. Eventually, you'd have to identify all the different comparisons, right? But consider groups A, B, C, D, E, F, and G, right? How many comparisons could we make? You'd have to be very methodical about it, right? Or use that that formula that was introduced, right? So here, how many groups do I have? I have 1, 2, 3, 4, 5, 6, 7 groups. Oh boy, here comes some math I don't want to do. How about I'll simplify it, I'll remove G and make it 6 groups. Sneaky. Who knows what 6 times 7 is? 6 times 5 I can handle. Yeah. But I get to do that. I get to make it easier on myself. So now if I have 6 times 6 minus 1 divided by 2, right? 6 times 5 is 30 divided by 2 is 15 possible pairwise comparisons. I haven't checked it out in a long time because we don't actually apply it here. So I don't know, but I would assume that in R you can just run something and it would figure out all the pairwise comparisons. It's clever enough to do that. So I have faith that it does do that for you. right? You wouldn't actually have to identify them all. But if you do, then you have to be working methodically. That's all I can say. So what can happen? You might reject H naught for the ANOVA and say, yes, there is something significant going on here, right? But then once you do these pairwise comparisons, it's totally possible that you don't reject H naught for any of them because you've made this adjustment, right? And so that doesn't mean that there isn't a significant difference. It just means that you would probably need to increase your sample size or something like that, okay? And I've just got one little screenshot here that I wanted to bring in here to summarize that. Oh, same page, I think. 294. 294. And I'm going to tighten this up here. Because it's the very last thing that I want to say for this chapter. And I want it to be, oh, now I made lots of room for myself. Want it to be on the same page. Okay, so it is possible to reject the null hypothesis for the ANOVA and then not subsequently identify differences in the pairwise comparisons. However, this does not invalidate the ANOVA conclusion, right? It only means that we have not been able to successfully identify which specific groups differ in their means, which is usually a sample size issue, right? But we'll leave it at that. All right. That's the end of chapter 7. Woohoo! So quiz number 4, which is on Tuesday. Not tomorrow. Yeah. Quiz number 4 material ends here. I did post, where is it? Ah, that looks weird. I'll change it so it doesn't look so weird. All right. I did post, so for ANOVA, I don't have a lot of practice problems. So I encourage you to check out the practice problems that are in the textbook. So at the end of the chapter, or the section rather, right? Here, they've got the chick weight example that I've kind of expanded quite a bit. I like using the chick weight data because it's really cute to think about, and it's in the base R package. And so you can just type in chick weight and it knows what the data is. So that's nice because then we can use it to learn stuff without getting too into R. And so, but also this coffee one is really good, right? Because this is similar to what I would ask of you, right? And so you know how to find the degrees of freedom. Given 2 sums of squares, you can find the third one, right? And then you can go through and you can find these values. So that's a good one. There's also the discussion sections, right? So there are practice problems in the textbook, but I wasn't gonna retype them all out. You can just look at the textbook, but maybe I should write that in my notes. See exercises at the end of section 7.5 for more practice. Okay. They're all questions that you can do. All right. Oh yeah, that's what I was showing you. So I did post the practice for quiz 4 because I had a lot of practice questions for this, not very many for the ANOVA. I think there's only one ANOVA on here, but I give you these so that you can practice at the very least just identifying what type of question it is, right? And then just kind of convince yourself that you can do it. Ideally, go through and do all the questions, obviously. I've posted the solutions. I do love this first question because there are so many different types of questions that we can ask, right? So each part, A, B, and C actually asks a different type of question, right? Or at least for a different group. So coaching companies claim that their courses can raise the SAT scores of high school students. Of course, students who take the SAT without paying for coaching generally raise their scores too. A random sample of students who took the SAT twice found 427 who were coached and 2,733 who were uncoached. Starting with their verbal scores on the first and second tries, we've compiled the summary statistics in the table below. So you've got the coached group, you've got the uncoached group, you've got summary statistics for try 1, summary statistics for try 2, but also you have the gain, right? Which would also be interesting because you have measurements on the same person, right? I did my try 1, I did my try 2. So now all of a sudden it's paired data, right? For the gains, right? So just depending on what type or what the question is. So did the students who were coached increase their scores significantly? Okay, so then you're talking about paired data. Is the gain for the coached students significantly different from 0, right? And so, or did the greater than 0, I guess, increase their scores significantly, depending on, oh yeah, it is try 2 minus try 1, right? So greater than 0 would be an improvement, right? So there's a lot packed into that little question. Did the students who were coached increase their scores significantly? There's a lot of thought process that goes into setting up that hypothesis. But then we could ask, is there good evidence that coached students gained more on the average than uncoached students? Now, all of a sudden you have these 2 independent groups, right? And you want to compare the gains for these 2 independent groups. Is the gain for the coached group significantly different from the uncoached group, or less or greater than or something? Gained. All right. Is there good evidence that there was a difference in the scores on the first try for the coached and uncoached students? Again, a 2 sample t-test, but using the try 1 data, right? So kind of fun to have this huge table, and you could try to come up with different hypothesis testing questions, right? You could do the same thing for try 2, that kind of thing, but just lets you flex your muscles a little bit. Okay, question 2 is the one where, I know, R code, but you can handle it. So let's see here. It's the chick weight data. And this is the one where I actually, so you have the mean, the standard deviation, the sample size for each of these groups. Part A is just a 2-sample t-test because I want to compare linseed and horse bean. Right, so that's fine, we can handle that. But then for part B, that's where I have these chicken feed solutions. Okay. And so here is where you would grab, so part A, I went through and I did, and then part B is the ANOVA, okay? And I know I didn't give you the output in the question, and that was weird of me. I should have done that, but that's okay. It's in here, right? And so that's why I say maybe just use the textbook for more questions on ANOVA, because here I just go through and show you how it would be done just in real life. Okay. But the ANOVA is actually quite small. I don't think I checked my conditions though. I never do. It's bad. But they're all the same, right? So you can do it. All right. I also gave you the RMD file, but you might have to copy and paste that into a new RMD file if you wanted to play around with it. So, because Moodle can't handle it.
Just be able to like right click it and save.
Yeah, right. And then it should save properly.
Should be able to open it.
I think, yeah, right. I did try it on my computer. I said I right clicked and then download linked file, but it wouldn't do it for me. So, but it has worked before. It should work, but it wasn't. Okay. Any questions for me? No? Is this the day I end early? Can you believe it?
I've got one question about the homework.
Hit me. Which one?
The p-value from software for question 7.
Mm-hmm.
I've tried a bunch of things. It's like a really low number, so I don't know if I'm messing up 0 or if I'm not even selecting something there.
Is it for the 1-sample mean?
It's for the 1-sample mean, but the correct p-value was between what the 2-sample mean value would be. Like I thought I was supposed to. 0.0005, but it wanted me to double it.
Is it assignment 15 or 14?
15.
15? I'll see here. It is entirely possible that I might have screwed up. Do you remember what question number?
7, I think. I tried both 38 and 30 degrees of freedom.
Mm-hmm. Should work with 30. I'll have a look because maybe I did something weird.
Because it asks for a 2-sided count for the p-value instead of 1, which would probably be based off of the hypotheses.
So when you find the p-value, are you multiplying it by 2 then, if it's a 2-sided
I
test?
tried multiplying it by 2 and it didn't seem to work.
Doesn't like it? Okay. It's starting to feel like an I screwed up type of deal. So let me see here. Maybe I can have a look. How do I? If you have some, oh, I guess I should stop the recording. Otherwise it's just me dilly-dallying. All right. If you have any questions, let me know, but I'm gonna stop this here. I think.